Hello students! Properties of logarithms. Know the following properties of logarithms and complete the table. If I could sum up what a logarithm is in a single word, I would say the word exponent. When I see the expression log base b of a, this represents the exponent needed on the base b to produce a. Which takes me right to property number 1. Log base b of a is the exponent c, because c is the exponent you need to put on the base b to produce a. This first property is just our equivalence of two forms of a relationship between a, b, and c. If b raised to the c is equal to a, this is called exponential form, then we know that log base b of a must be c, and this is called logarithmic form. For example, log base 2 of 8 is a number, and that number would be the exponent needed on 2 to produce 8, and of course that number is 3. And its exponential version would be 2 raised to the 3 is equal to 8. Now, in general, you want to be very comfortable being able to go back and forth between log and exponential forms. Property 2. Log base b of 1 is 0. This will always be true for any legitimate base. Remember, the base of a logarithm must be positive, but can't be 1. For example, log base 7 of 1, this would be 0, because 0 is the power you need on 7 to produce 1. Property 3. Log base b of b is 1. So when the base of the log and the argument of the log are equal, then this logarithm will simplify to 1. For example, log base 5 of 5 is 1, because 1 is the power needed on 5 to produce 5. Number 4, log base b of b to the a is just a. For example, consider log base 2 of 8. Of course, we did that right here. The answer will be 3, but watch this interpretation. 8 is the same thing as 2 cubed. Sometimes it's helpful to put that argument in parentheses. And when you're trying to figure out what this logarithm is, and you set this up in exponential form, you say, what power would I put on 2 in order to produce 2 cubed? The answer is staring us in the face. That power needs to be 3. So when you have a base of a logarithm, and then the argument of the logarithm is also an exponential with the same base b raised to the power a, then log base b of b to the a will cancel and give you just a. This is very much related to the fact that logarithms and exponentials are inverse functions of each other. And so when you compose them, they cancel each other. It's like squaring a square root, or square rooting a square, or cubing a cube root. These kinds of operations reverse the effects of each other. Property 5 is also a composition of an exponential and a logarithm of the same base, but composed in the other direction. This is the log function, base b, being plugged into as an exponent into an exponential function. And we get cancellation and we get a back. For example, consider 2 raised to the log base 2 of 8. Well, first, do log base 2 of 8. What power is needed on 2 to produce 8? And the answer is 3. So that exponent simply becomes 3. But now we're going to put that exponent as a power on 2 again, and naturally it should reverse us right back to 8. So log base 2 of 8 is the power needed on 2 to produce 8, and then if I put that power on 2, I better produce 8. This would even be true if I couldn't do this intermediary step. For example, if I did 2 raised to the log base 2 of 5. Now this logarithm is not easy to simplify. It exists, it's an irrational number with a decimal representation that goes forever, but I don't need to figure out what that decimal is. 2 raised to the log base 2 of 5 will always just produce 5, because log base 2 of 5 is the exponent needed on 2 to produce 5, and if you then put it as an exponent on the base 2, you should just go right in a circle and get 5. So b raised to a logarithm, if that logarithm has the same base, then the argument of the log becomes the simplification of this expression. Property number 6. This property is very much related to a property of exponents that says if you multiply two exponential situations with the same base x, but maybe different powers, 2 and 3, then the new power is the sum of 2 and 3, in other words, x to the 5th. So the exponent of the product, 2 plus 3, is the sum of the exponent of the first factor plus the exponent of the second factor. And when you recognize that logarithms produce exponents, so think of this as saying the exponent of a product is equal to the sum of the exponent of the first factor plus the exponent of the second factor. So whenever doing log of a product, you simply do log of the first factor plus log of the second factor, and of course add them together. Property number 7, if you have an exponential situation, so something raised to a power, and you divide by another, and the bases are the same, if you recall from properties of exponents, we can do the upper power minus the lower power to create a new power. So the exponent of the result of this quotient is the upper exponent minus the lower exponent. In terms of logarithms, that would read the exponent of a quotient is the exponent of the numerator minus the exponent of the denominator. So saying that same thing in terms of logs, logarithm of a fraction is log of the numerator minus log of the denominator. Property 8. Property 8 looks a lot like property 4, but in property 4, we had a log base b of an exponential statement, where that exponential statement had a base that matched b. But in property 8, we have a log base b, but of an exponential whose base is no longer necessarily b. So we have an a raised to the c, and the a and the b don't need to match. But what we can do is that exponent c, this exponent c can be brought down as a coefficient of the logarithm instead, giving us this result. You can also do this property, and any of these properties for that matter, backwards. Like in property 6, if you see the sum of two logs, you can condense that into a single logarithm by multiplying the arguments. Or if you see a difference of two logs, you can condense this into a single logarithm, but of a quotient. And if we start with a number times a logarithm, you can grab this coefficient c and bring it up and put it as a power on the argument. And now property 9. Property 9 has a name. It's known as the change of base formula. If you have any logarithm of any base of an argument, you can write this in terms of logarithms of a new base by writing this fraction. We do log base c. Now you get to choose a new base c. It could be any base that's a legitimate base, so positive but not 1, divided by another log of the same base. And the argument of the numerator log matches the argument of the original log, but the argument of the denominator log is what used to be the base of the original log. And again, you get to choose c. C must be positive. C can't be 1. So you can choose base 3 and write it this way. You can choose base 10. And if I choose base 10, I don't need to write the base, as we discussed in last lesson. A logarithm whose base is not written is base 10. Or you could choose base e. Log base e is what we call the natural log, ln of a over ln of b. And this list, of course, would go forever, because there are infinitely many choices you could make. Now, a goal of yours should be to use these properties so often that they eventually become natural to you, and you use them fluently without needing to look them up. Now, this first column I'm referring to as the general log properties. That's because I kept all these bases b unspecified. I could rewrite all these properties for the specific case when b is 10, and that, of course, is the base that you would have for what's called the common log. So rewriting property 1, where the b's are specifically 10, would read log base 10 of a is equal to c, double implication, 10 to the c is a. Now, when you write a log base 10, you actually don't need to bother writing the base 10. So you can write this statement. Now, of course, this 10 needs to still be there because it's not written in the context of being a base of a logarithm. It's a base of an exponential. Property 2 would be log base 10, and I won't write the base, but just that log of 1 must be 0. Property 3 would be log base 10. I don't need to write that base, but the argument needs to be 10 as well. And the argument you must always write. So log of 10 is 1. Property 4 would read log base 10, and don't write the base, but the argument is 10 to the a, and this will always just simplify to a. Property 5 would read, the b that is the base of the exponential must be written explicitly as a 10, but then raise it to the log base 10, and that 10 I don't need to write, of a, and this will always simplify to just a. Property 6, none of these b's do I need to write, because they're all bases of logs. So this would read log of a product, and you don't need to necessarily write that product in parentheses, as long as it's obvious that the argument of this log is ac. But this would equal log of the first factor plus log of the second factor. Property 7. The parentheses here are optional, as long as you recognize that a divided by c is the argument, and if that's the case, you can do log of the numerator minus log of the denominator. Property 8. Log of a raised to the c can be written as c times log a. Looks like clog a. When you look at this, we have nothing but letters. It can be confusing, but this has distinct meaning. It's the number c times the logarithm base 10 of the argument a. So this dot in parentheses could help break that up into a more sensible looking expression. And property number 9, if you start with just log a, you can still use change of base and say this will be equal to a fraction of 2 logs. The argument of the numerator log will be the argument of the original log, but the argument of the denominator log will be what used to be the base of the original log, and that base is not visible, therefore it's 10. And then on these two logarithms here, you can put any base you want. I'll just write c. And now the natural log, this is a logarithm whose base is e, which is Euler's constant, about 2.7, but the decimals go forever without pattern. So again, all the b's in my general log statements, I'm going to change to e's. So property 1 would read, log base e of a is equal to c, double implication arrow, e raised to the c must be a. Now log base e has a new notation though. We write ln. I like to use cursive when I write ln. So the natural log of a equals c implies that e raised to the c must be a. Property 2 would be log base e, which is the same thing as natural log, of 1 must be 0. Property 3 would be log base e, or natural log, of, and the argument you must write, and the argument must be e, and this will simplify to 1. Property 4 would read log base e, which is natural log, of e to some power. This will always simplify to that power a. Parentheses on the argument are optional. I think they're useful when the argument starts to get more complicated. Property 5 would read e raised to the log base e, and I write ln instead, of a, and this will always simplify to just a. Property 6 would read natural log of a product is equal to natural log of a plus natural log of c. Property 7, natural log of a fraction equals natural log of the numerator minus natural log of the denominator. Property 8, natural log of a raised to the c can be written as c times the natural log of a. And property 9, if you begin with a natural log of something, you can use the change of base and write this as a fraction of logs. The argument of the numerator will be the same argument a. The argument of the denominator will be the base of the first log on the left, and that base is e. And then for these two logarithms you just wrote, you can choose whatever base you want, as long as it's positive but not 1. Okay, there is a lot going on this page, and your goal should be to practice them so much that they become second nature to you. Okay, let's go to the next page. We have the 9 general logarithms here summarized on the left for easy reference. And we're going to express each of these 6 expressions in a new way using log properties. And the goal here is simply just to practice recognizing when log properties can be used and how to use them correctly. I'm also going to use this numbering system so I can easily identify which property I'm using when I make a change. Okay, log base 2 of 4 to the x. Our argument is an exponential situation. So that makes me think property 4 or maybe property 8. The base of this log is 2 does not match the base of the exponential that's in the argument of the log. That's true in the case of property 8. So property 8 will be my focus. I'll put a little 8 above this equal sign, suggesting I'm using property 8 right now. And so this exponent that's on the 4 can be brought down as a coefficient instead. So we write x times log base 2 of 4. Now I'm going to simplify log base 2 of 4. To do this, you would say, well, what is the exponent needed on the base 2 to produce 4? And the answer to this, of course, is 2. So this logarithm will simplify to just 2. But let me show you this. I'm going to rewrite 4 as 2 squared. Because now I see a log base 2 of 2 to something. That matches property 4. And property 4 says that we should just get this a back. So all of this will simplify to that red 2. Because we have, in effect, a cancellation of log base 2 with that base 2, leaving the exponent 2 only. And this, of course, was using property 4. Notice I did not put a property above this one because I did not use a property in that step. And then naturally, I would write this as my final answer, 2x. Right, this next one, I noticed this power 2 right here. And just like this power x up here, and then we were able to use property 8, it makes me think I can use property 8 right away. But you must be careful. This exponent 2 is only an exponent on the x. It's not an exponent on the 4. In reality, this is a 4 times an x squared. This is what the argument is as far as order of operations is concerned. Property 8 can only be used when this power c is a power on the entire argument. And currently that's not the case. This power 2 is not a power on the 4 and the x both. So instead you want to think of this argument as an a times c situation where the a is 4 and the c is x squared. That leads me to wanting to use property 6. So property 6 will be used, and we're going to write this as log, and notice there's no base written, so this is log base 10. I don't need to write the base of the first factor, 4, plus, and then that same log base 10 of the second factor, x squared. Now this logarithm does not simplify nicely. There's not an easy power to put on 10 to produce 4, so I'm going to leave that alone. But here I do have a power on the entire argument. This is where I can use property 8 to bring that 2 down. So this whole expression will equal to log 4 left alone plus, and that 2 will drop down as a coefficient, times log x. And that was property 8 being used. Next one is log base 10 again of a quotient. The argument here is a fraction. That is clearly a case for property 7, which tells me that I should be able to write this as log base 10 again of the numerator minus log base 10 of the denominator. Now I could take this a little bit further because the square root of x is just a power of 1/2. And once I interpret that radical as a power, I see a power on an argument that I can now bring down to the front using property 8. and write 1/2 log x minus log y. Now, if I start with this expression, I can use property 8 backwards to go to this line, and then I can simply interpret x to the 1/2 as square root of x, and then I have a difference of logs that I can use property 7 backwards and condense that into a single logarithm. And we want to be comfortable going forwards in this process and going backwards in this process. In fact, this next one allows us to go backwards. So I have two natural logs being added together, but one of them has a 3 in front and the other does not. Look at property 6. Property 6 is the sum of two logs of the same base, but both of the logs have implied 1 coefficients. Well, this logarithm has a 3 coefficient. Well, property 8 has a coefficient of a logarithm, and it allows me to bring that c up as a power on the argument. So I'm going to use property 8 first, where I bring this 3 up as a power on that x. And we write natural log of x cubed plus natural log of 5. Now I'm in a position where I can use property 6 backwards. So property 6 will allow me to condense this into a single natural log, and my new argument will be the product of the two arguments. So I'll put the 5 first and then the x cubed. Now the next example, here we have a fraction of two logs, not to be confused with a single log, but of a fraction. But in this case, where you're dividing two logs, we're actually going to use property 9, but backwards. Remember one variant of property 9, if I choose both these bases to be e, would read natural log a divided by natural log b. And when you divide two natural logs, you can condense this into a single logarithm using property 9 backwards. So this will become a new log, no longer a natural log. This argument 2 will become the base of this logarithm, and this argument 8 will become the argument of my new log. And this was property 9. And now that I've done this, I can simplify log base 2 of 8, so this logarithm produces 3. And this last one, 7 raised to the log base 7 of 6. Notice that we have 7 raised to a logarithm, and that logarithm has the same base. This is where property 5 is going to apply. So 7 raised to the log base 7 cancel, giving us just a 6. Now I want to give you some warnings about some common mistakes that students make. If you have a log base b of a sum, one common mistake is to do the log of the two addends separately, some sort of distribution, and write. And this is not true. It can easily be disproven by letting both a and c be 4 and b be 2. On the left side, we get log base 2 of 8, which turns out to be 3. And on the right side, we get 2 plus 2. And these are clearly not equal. Similar for log base b of a difference. You cannot do log base b of a minus log base b of c. If you have log base b of a product, sometimes I see the mistake of writing this as the product of the logs. Make sure you do not make this mistake. If you have log of a product, you would instead use property 6. Another common mistake is if you have log base b of a fraction, that you write this as the fraction of the two logs. This is also a common mistake. If you have log base b of a fraction, you should instead use property 7. And if you have a fraction of logs, you should use property 9. Okay, moving on to the next page. Expand the logarithmic expression as much as possible. So we have a single log expression, log base 5, and all of this is its argument. It's a very complicated argument, but it's also a fraction. So I'm going to begin by using property 7, because we have log of a fraction. So this will be equal to log base 5 still of the numerator minus log base 5 still of the denominator. And I'll put all my arguments in parentheses as long as they are still complicated arguments. All right, next, I see we have log base 5, but of a product, 25 times radical x. And again, we have a logarithm of a product, x cubed times x minus 5. So I'm going to use property 6 twice in this next step. So we have log base 5 of the first factor plus log base 5 of the second factor, and then minus. I will use property 6 on this logarithm expression. So we have log base 5 of the first factor, which is x cubed, plus log base 5 of the second factor. Definitely need to keep this one in parentheses. If you don't keep it in parentheses, that could be interpreted as log base 5 of x, and then after the fact, minus a 5, which we don't want. The argument is x minus 5. Now here's the danger. I use property 6 twice, but this minus sign that's in front of this would need to distribute. So put this in parentheses. In the next step, I will do the distribution. Log base 5 of 25, we'll recognize 25 is 5 squared, plus log base 5 of x. I'm going to change the square root to a 1/2 power. And now I'm going to distribute the negative. So we have subtraction on both these logarithms. Now I could use property 4 in this first log and cancel the log base 5 and the 5 and just get a 2. Or if you fail to recognize property 4 applies, you can just use property 8 And all three of these powers are going to drop down as coefficients using property 8 3 times. So we have a 2 log base 5 of 5 plus a 1/2 log base 5 of x minus 3 log base 5 of x. And the last log stays the same. Now I'm going to ask myself, log base 5 of 5 is what number? That's equal to a 1 using property 3, because 1 is the power needed on 5 to produce 5. So in the end, this whole first term will just become a 2. Now you might have recognized that much earlier by simply looking at this logarithm and saying, what power is needed on 5 to produce 25? And that answer is 2. With these properties of logs, you will eventually discover that there are lots of different ways that you can approach a problem. I also recognize that the two middle terms are similar. They're both multiples of log base 5 of x. So to combine them, I need a common denominator on their coefficients. So this 3 I'm going to change to 6/2. So we get 2. And now we do positive a half minus 6/2. It would be minus 5/2 log base 5 of x, and then minus log base 5 of x minus 5. And we'll consider this done. Now notice up here in the original, there is a potential for simplifying the original fraction from the start. The square root of x divided by x cubed could have been simplified to begin. 1/2 minus 3 is negative 5/2, which is 1 over x to the 5/2. So this original setup I could have rewritten first as log base 5 of 25 over x to the 5/2 times that x minus 5, and then proceeded to use log properties, and we would get this same final answer in the end. So again, illustrating that there are multiple paths to take when working with log expressions. All right, this second example condensed the expression into a single log expression. Notice we have a bunch of natural logs, and then we have a minus 6. Let's first tackle the natural logs. These first two terms are being added together. One of them has a coefficient of a third, so I'm first going to do property 8 and bring that 1/3 up as an exponent. So you have natural log of a plus natural log of b to the 1/3. And while I'm at it, I'm going to move that 7 up, but leave the minus sign as subtraction. So we have minus natural log of a plus b raised to the 7, and then minus the 6. Now I'm going to use property 6 backwards on just those first two. So that can be written as natural log of a times b to the 1/3. Now I see a subtraction of two natural logs, so I'm going to use property 7 backwards and write this as a single natural log of a fraction. The numerator will be ab to the 1/3, and b to the 1/3 is the cube root of b, if you want to write it that way, and then divided by the a plus b to the 7. And then we still have this minus 6. Now we were supposed to condense the expression into a single log expression. Currently, I'm not quite there. I'm going to rewrite this 6 as the natural log of e to the 6. That's using property 4 in the natural log context. Any number you want, you can rewrite as natural log of e raised to that number. In this direction, it feels like a simplification. In this direction, it feels like a complication of the expression. So property 4 gets credit for doing that. And the reason I did that is because now I have a difference of two natural logs, and I can use property 7 again. Log of a fraction, where the numerator is the first argument, and the denominator will be this second argument. And this is an unpleasant complex fraction here. So think of the second argument as being over a 1. So instead, multiply by the reciprocal of e to the 6th. And then, of course, you can push these together into one fraction by multiplying the numerators and multiplying the denominators. And we'll consider this now finished. You might have also started to pick up on some generalities. If you have any log, I'll just write log base 10, but this could be log of any base, and a complicated product / quotient with exponents and all the different factors, that using properties 6, 7, and 8, that this will wind up being the following. The n exponent that's on the a will become the coefficient of a log of a, plus, we do something similar with the b to the m log b, and then we do something similar with the two expressions in the denominator, but both of them will have minus signs. So minus x log c minus y log d. Both of these will be subtraction. Like we saw up here, both of these were subtraction because this negative sign had to distribute. Next page. Use properties of logarithms to show the following statements are true. So I'm going to begin with the left expression, which looks more complicated, and I'm going to see if through a series of log properties I can produce the right side of this statement. All right, first thing I'm going to do is use property 6 on this sum of two natural logs and write this as natural log of 2 times 5, which is, of course, just 10. And now I see that we have a fraction of two like logs, which will allow me to use property 9, the change of base property, and write this as a single log where the argument 10 will become the base and the argument 4 will stay the argument. But log base 10 of 4 is what log of 4 is without a base. So check. Now for the other one, I will begin again with the log of 1/2. This is log of a fraction. This makes you want to use property 7 and write this as log of the numerator minus log of the denominator. And now this logarithm will simplify to 0 because 0 is the power needed on the base 10 to produce 1, which is property 2. Log of any base of 1 will be 0, including in this case where the base is 10. Log of 1 is 0. So giving credit to property 2, we get 0 minus log 2, which is of course just negative log 2, and we have arrived at our right side. There is another way to do this. 1/2 can be rewritten as 2 to the minus 1, not using a log property, just a property of exponents. And now I can use property 8 to bring this minus 1 power down as a coefficient. And that takes me right to what I want, negative log 2. Being able to have multiple expressions for the same logarithm is important because there will come times where one solution pathway takes you to this answer, a different solution pathway maybe takes you to this answer, and at first you might say, oh, I got different answers, but in reality, there are lots of different ways to represent a logarithm, and what appears to be different looking expressions might in the end be the same. Now, older calculators could only calculate common or natural logarithms. Thus, the change of base property, which is property 9, was helpful for calculating logarithms with bases other than 10 or e, which are the bases of the common and natural logs. But modern calculators can calculate logarithms of any base. Determine what two consecutive whole numbers the logarithm below is between. Then use the change of base property to express the logarithm in terms of both common and natural logs. Then use technology to show that all three representations are equal and that the result is as predicted. All right, log base 7 of 52. This represents an exponent needed on 7 to produce 52. So 7 squared is close, but it's lower than 52. And 7 cubed, without even calculating it, we know is more than 52. That tells me that the exponent I'm looking for must be somewhere between 2 and 3. So this logarithm is somewhere between 2 and 3. So log base 7 of 52, using the change of base property, we'll write this as a fraction of 2 logs. The argument of the numerator will be 52, and the argument of the denominator log will be the 7. And then you get to choose whatever base you want. And I'm going to choose base 10, which is the common log. In other words, I don't need to write any more. Or I could have used log base e's, in other words, natural logs. And again, 52 and 7 would be the arguments. Now we're going to compute all three of these expressions using Desmos as our calculator and show that they all give you the same decimal in the end. So here's log base 7 of 52. It's about 2.03. Here's log base 10 of 52 over log base 10 of 7, or you can simply just say log 52 over log 7. And again, we get the same decimal, which is about 2.03. And here's natural log of 52 divided by natural log of 7. And again, we get the same answer, which is about 2.03. Again, it means that if one student gets this answer, another student gets this answer, your first instinct should not be that one of you is wrong, but perhaps that these answers are in fact the same, just different representations of them. And we get an answer 2.03, which is as predicted between 2 and 3. And of course, it's much closer to 2, because 7 squared was much closer to 52 than 7 cubed would have been. And this concludes our lesson on properties of logarithms.